Hey folks, like thank you so much for joining. So this stream is gonna be no, this is not another fake gaming stream. Exactly. So I'm super glad to announce this is actually a technical stream. So we're gonna be looking at how NumPy works, right? And so I think there's lots of interesting ideas with NumPy. So without further ado, let's just get started. So just let me drop some stuff for you. It'll make it very clear what we're doing, right? So first off, like it's like, well, why is Mark talking about NumPy, right? Like actually, originally, like, I thought about talking about NumPy because some people on Discord suggested I talk about XLA instead, but I thought talking about NumPy would be a lot more useful, and here's why. So NumPy is basically, it's really like they say it's a library for scientific computing, but really what it is a library for basically working with tensors, like work with like tensors, which are like large dimensional matrices. So a natural question you may ask, well, what's PyTorch, right? And like, well, what are PyTorch and TensorFlow? And I think the best way to explain what they do is they're basically NumPy plus GPU acceleration plus autograd. So basically automatic differentiation so that you could get the gradients of some loss function. So so you can like learn in deep learning. And so really, I mean, so that's more from a technical standpoint, but from a more of a, sorry, so that's more from a customer standpoint. PyTorch like focuses and TensorFlow focus on deep learning researchers, and this NumPy has a broader scope in terms of its customers, which is people that deal with scientific computing. Okay, so if you look back at NumPy, it actually has a Python. So there's a few aspects to NumPy, and I think we'll go over. We're actually going to go over all the stacks. This is a good outline of what we're going to be talking about today. So one is actually the NumPy, basically. So sorry, not so basically. Let me say this. So you have like the matrix manipulation in Python, right? Which then calls some code in C++. Of course, hysterically laughing. It's okay. Run, quick. Okay. So you have some code in C++, and what ends up happening after that is the actual matrix multiplication API in C++ is controlled by this thing called LAPACK, which we're going to go over, which then leverages some very core kernels written in assembly in a protocol called Blas. Right, so these are sort of like the four steps involved. Like basically, this is sort of like the NumPy hierarchy, right? And at a high level, like I think the deeper we go down the stack, it's like, I mean, let's see, how should I do this? Should I go depth first or breadth first? Hmm. Okay, let's do breadth first, right? So here you're basically dealing with stuff like matrix multiplication. You're dealing with like indexing, like stacking, like basically like the API that you would typically use in NumPy or TensorFlow, like or PyTorch or whatever, so the stuff that you're familiar with. And then basically there's sort of the same thing here. Like basically in LAPACK, you're also going to have similar things. Like you're going to have matrix multiplication, you're going to have indexing, you're going to have stacking, etc., and everything else. And at the very end here with Blas, what you're going to have is some assembly functions for what are called core kernels. And so what do I mean by that? So let's say we're gonna have some hard-coded assembly to basically multiply 2 by 2 matrices, 4 by 4 matrices, 8 by 8 matrices, and then pretty much what like the last thing that we need to talk about is, well, why is Blast fast, right? So and it's old, by the way. So why hasn't no one changed it like in all this time? So it uses a few core ideas that we'll go over them one by one. So There's pipelining, and the idea behind pipelining is that you can have multiple instructions executing at once on your CPU, and they're sort of running in parallel. Um, and then like that way that your instruction module isn't blocked basically. Like they can keep doing other stuff while waiting for the full set of instructions to finish. There's vectorization, which is essentially parallelizing instructions. So like imagine you're doing something like a dot product. Let's say you're doing this, right? So you have these two matrices, these two vectors, sorry. And what you basically want to do is multiply this entry by this entry, this entry by this entry, this entry by this entry. And so the idea behind vectorization is, well, since these instructions are embarrassingly parallel, can you sort of on a separate thread do this? So basically this will be on thread 1, this will be on thread 2, this will be on thread 3. And so this happens like completely concurrently. So there's and then the last idea that I think is super important is caching. And so imagine this. So like let's say we're dealing with like this is a matrix, right? And this is another matrix. So when I'm on this row, I'm going to be multiplying, like, so I get the result. I'm going to multiply this row by this column, then this row by this column, this row by this column, right? So I need this thing to stay in cache, right? And so making sure that like it fits in cache, or like let's say the row is too long, well, maybe I can break it apart so that it can fit in cache. Like these ideas are going to be super important for matrix multiplication, because the naive implementation of matrix multiplication is big O of n cubed. Which just means it's insanely slow. Like, I mean, for anything reasonably large, you're just going to end up waiting too long. So, okay, so this will be like an outline, I think, of what we're going to be doing. Hopefully I didn't block this here. So this is going to be an outline of everything. Can you explain assembly again? Yeah, maybe I'll just show you actually, and then I can get to this idea here. Let's see, so Openblast. Let's say so Openblast is basically what these instructions will look like. So I go on Openblast, GitHub, and then let's say I'm going to say dot product, for example. Okay, so it's called .c. Okay, no, that's the benchmark for it. Where's the kernel? So yeah, so you see there's a kernel for various architectures. So some is for ARM, so like stuff that runs on mobile devices. MIPS is a classic architecture used mostly for educational purposes, as far as I can tell. x86 is what you're probably using if you're using a gaming PC. And then there's other ones like RISC, CISC, like PowerPC is the old Mac architecture. So again, this is a very important thing, right? Like these libraries need to work over multiple computer architectures and use whatever kinds of vectorization, pipelining, caching mechanisms they have. And so I'm just going to pick x86. And you'll notice it actually looks like this. Like this is very core instructions. I mean, you're basically literally saying stuff like, you know, load this thing to this register, multiply this register to that register. And so this is one of the reasons why no one touches this thing. And even though we've had so many scientific computing libraries since, like, you know, we have TensorFlow, PyTorch, JAX, you have like the Julia ecosystem, we had Torch, we had Theano, we had like Cafe2, like there's just like an infinite, like probably there's a bunch more that I missed. And the idea is that all of them under the hood would leverage the same kernels. So for example, this is what a dot product would look like. But then I believe here, like, let's quickly go through it. Let's see. Kernel, yeah. So kernel. And then, where's x86? x86. And then do we see something like a matrix multiplication? Yeah. So GEM means generalized matrix multiplication, right? So you'll see here that there's a bunch of kernels specifically for multiplying 2x2 matrices or 2x4 matrices, right? So, you know, let's say, what does let's pick 2x2, for example. Again, literally looks like this. You know, like I'm not going to go through this. It's probably fairly messy. But long story short, like the C++ code version of this thing will basically just have a function that takes in a matrix where the matrix needs to be 2x2. And then this is pretty much like the fastest way of running it while taking advantage of the x86 architecture. I think more detail than this, I would need to do a separate stream about assembly and about various nuances in computer architectures, which I'm not aware of. Like, I mean, like that's just not something I really do or know about, but just something to keep in mind, right? And that, like, let's say, yeah. So it's called Openblast for a reason, right? It means it's open source. And that's because Blas is actually is a protocol and its implementations may not be open source. So for example, let's say Blas for Intel, right? So you're going to have something like this, like the developer reference for Intel. And Intel will tell you how to use the libraries, but they're not necessarily going to tell you how they're implemented, right? And so the main thing to keep in mind with Blas is that there's sort of three layers to it. The first one is like what are called like level one routines, which is how do you multiply, like vector to vector operations. So like a dot product is a great example. You're multiplying the individual entries. This is very parallelizable. So how do you do this very fast with SIMD? The other one is matrix vector. So basically, I would imagine the idea is you cache the vector, and then how can you do smart traversals over the matrix and parallelize the instructions over the columns or the rows of a matrix. And the last, like level 3 routines, are matrix to matrix operations. So this is generalized matrix multiplication, which we're going to talk about like in the tiled matrix multiplication algorithm, which I'll cover in a bit. And then this is more recent, right? But the idea behind sparse matrices, I've talked a lot about them in my deep speed video and a bunch of other ML compiler streams. But the idea behind sparse matrix multiplication is that, like, let's take something like, I don't know, like the Netflix problem, right? Which is a matrix where you have users and the movies they liked, right? Most people haven't watched all movies on Netflix, so most of the entries of that matrix are going to be 0. So how can you still end up having fast matrix multiplication in that setting, which is more common than the dense one? Uh, right. So you may also be wondering, like, I mean, like, why is Mark only talking about matrix multiplication, right? Like, and so one point I really want to make, like, because I had this as a meme in one of my articles in The Great Stagnation, where I said like matrix multiplication is all you need. So why did I say this? So let's take like a couple of architectures, right? So if I say like matrix multiplication is all you need for deep learning, then really what I need to prove to you are like that 4 things are actually matrix multiplication. So one is basically MLPs, and these are basically linear layers, right? You have RNNs. These are also linear layers. I'll show you how in a second. You have CNN. They can be linear layers with a trick. And then you have transformers, which are 3 linear layers. I think this is also 3 or 4. I'll show you the code now. So let's go over them one by one, right? So let's say an RNN, for example. So sorry, this is an LSTM, for example. And so notice here is that an LSTM typically has this sort of complicated explanation that talks about like how there's sort of like a recurrence, and it seems like this like crazy graph that you're unrolling. But fundamentally, the idea is that there's certain stuff that you don't want to forget. And so you're going to have what's called a forget gate that helps you forget stuff. And then you're going to have some sort of input. You're going to have your cell, which represents like your memory, and then an output. And so you notice like all of these are linear layers that go from like the number of inputs to number of hidden layers to the number of hidden layers, right? So let me just quickly show you what a linear layer actually looks like. So a linear layer is basically a function of the form xa plus b, where a is a matrix, right? So this is sort of like the fundamental operation that you're doing whenever you're working with a linear layer. And obviously, if you're composing them, then that you're essentially composing them via matrix multiplication. And this is why matrix multiplication is just such a fundamental operation in deep learning. But let me show you some other tricks like that you may not be aware of. So let's say, for example, I'm using the Hugging Face transformer library, right? And so BERT sounds like a complicated example. Like it sounds like, okay, what is this thing called? Attention, and then there's the key and the value, etc. So let me just actually show you what this looks like, and you'll be convinced that like, oh, wait a minute, maybe this thing isn't all that complicated. Here, so where was it? Here. So let's say, so this is going to be the model. So we're going to get the BERT base model, which is sort of like the hello world of BERT models. It's not that small actually, but it's just something to keep in mind, and that like this is sort of like a good baseline for everything. Like this or distill BERT, I would argue, are probably the baselines for a lot of deep learning stuff. So I'm downloading the model right now. So you'll notice it's about like 400 megs. So it sounds like it's a sizable model. It's not like tiny or huge, but let's say, so if I print the model, what does it look like? So you'll notice that there's a bunch of layers. So, right, so we have these embeddings. So think of embeddings as some sort of like key value store. And then we have this attention layer, right? And then what an attention layer it basically consists of the squarey matrix, the squarey, which is a linear layer, a key, which is a linear layer, a value, which is a linear layer, and then dropout, which basically is an operation on top of those layers that would drop certain elements so that the training is more robust. But strictly speaking, you actually don't need this dropout. It's just something to make the training like a bit more stable. But the idea is still here. Like, I mean, again, this is all linear layers. And as far as like matrix multiplication goes, sorry, as far as convolutional neural network goes, like that one feels a bit different, right? It doesn't naturally seem to fit the linear layer paradigm. So I actually had the example here on Discord. Where was it? Here. So there's this thing called the Topolis matrix, which is basically a transform. So you can turn a convolution operation into a matrix multiplication, right? And so it looks something like this. I'm not going to go over how it works exactly, but suffice to say is that this means that, let's say you are trying to support a deep learning library. This means that you need to basically offer good out-of-the-box performance for the kinds of models that your users care about, which today are multi-layer perceptrons, RNNs, CNNs, and transformers. All of these fundamentally are about matrix multiplication as the core paradigm. So what you end up going to doing is you need to make sure that that operation, which is going to be the most time-consuming part of your entire model run, is going to be as fast as possible. And the way you're going to do that is you're going to leverage the libraries that accelerate the stuff the most. So you're going to use Blas. So this is how Blas comes into the picture. And Blas is there. You know, there's closed source Blas, which is what Intel does, but obviously Intel doesn't support like architectures that they don't own. And so that's why it's really important to have stuff like Openblast, which is, you know, gives you sort of like an API to work over multiple ones, and gives you just a general idea. And so then again, when you're thinking of, well, what value does PyTorch add or TensorFlow add? Well, they provide a similar kind of acceleration for matrix multiplication on GPU, which are much faster at running matrices for other reasons, basically tensor cores, CUDA streams, streaming multiprocessors like FP16, FP32 units. You know, there's a whole bunch of tricks we could talk about with GPUs. And AutoGrad. So NumPy doesn't support AutoGrad out of the box, but I'm pretty sure there's people that have libraries to make NumPy work with AutoGrad. But basically, when you're thinking NumPy with AutoGrad but with AutoDiff, you're essentially thinking of a deep learning library. You're no longer just thinking of NumPy. Right? So back to this. So this is sort of like, so what did we do so far? So we just said, well, everything's a linear layer. And we need linear layers to be really fast. Linear layers are matrix multiplication. And we talked about how Blas has like some assembly code to make this really fast. But let's just, you know, maybe go over more basic stuff. Like, let's say, so yeah, I mean, so here, so this is, let's say Intel, they'll show you, okay, well, you know, we have this thing called the dot product operation and MKL. So MKL is their library to do accelerated, I forget what, the math kernel library. And see, it's in Fortran as well. So a lot of this code hasn't changed for decades. It's still the same. And it works over, let's say, double precision, average precision, real numbers, and then they can add all sorts of optimizations. Like maybe you want to make it work over int 8, or you want to make it work over float 16. Oh, thank you for the subscribe. I appreciate it. Oh, Science Lover. Nice to see you. So yeah. So this is just like at a high level, gives you a sense of sort of how the entire ecosystem is built out, like from one matrix multiplication all the way to Blas. So just to show you a bit more, like when I talk about NumPy, and if you are trying to create a new linear algebra library from scratch, like what is it that you really need to build out, right? So let's say if we go to NumPy on GitHub, the first thing you'll notice is actually a very popular library. Like, you know, it has like about like 20K stars. It's had over 1,000 contributors over its life, which is insane. And you'll see here, like most of the code seems to be written in Python. It's like 60%. And then there's about 35% of it that's written in C, right? So in the C part, I'll talk about this in a second, but let's just go over just the basic Python stuff, I think, first. I think will be super helpful. So in general, like we talked about this, right? So let's say you want to do a dot product. Well, this is what you're doing, right? But if you want to do a matrix multiplication, this is what you're doing. So this operation is going to take, so here there's a single for loop, right? So this is going to take a time n. Here there's two, so in the case of our 2D array, I think this is multiplying no, it is multiplying two matrices, right? So I talked about this stuff already, but if you're wondering, like, well, why is NumPy fast? The main contributions are vectorized code. So again, vectorized code is some operations are embarrassingly parallel, especially the ones over vectors. So being able to parallelize those and run them at the same time on a processor is going to be faster. They're also saying, well, the code looks more mathematical, and we use more Pythonic code. This is not necessarily why it's fast. I think really, I think what they should have said is this plus Blas is what makes it fast. But here, so the main object in NumPy is what's called an ND array. So an ND array is a matrix or a tensor, and it's going to have a shape, which is the dimensions, right? Like, is it, how many rows does it have, how many columns does it have, like what's the number of elements that it has, and the type of the data. So like basically, is it float 16, float 32, is it int 8, whatever it is. But this gives you a good idea of, like, let's say as a thought experiment, right? You're multiplying two matrices on CPU, and you notice it's very fast. And you go like, okay, great, but like I'm multiplying with floating point 32, but if I used int 8, this would probably be a lot faster, right? Because after all, int 8 is smaller. And then you run it, and then it says, well, actually, this operation isn't supported for int 8 for your specific hardware, so that means you need to go implement it yourself. And then you need to go figure out, well, why is it not implemented? Is it not implemented because no one got to it? Or is it not implemented because the hardware itself doesn't have support for accelerating those kinds of operations? And again, like, this sort of lower precision math became more popular more recently with deep learning. But certainly for scientific computing, like, floating point 16 is not acceptable, because if you have small errors in your predictions, you could predict that the world's going to end tomorrow versus, like, 100 years from now, and that will change your policy, so it's not good. But for deep learning, it's actually totally fine, because you have, like, more weights to your model, more parameters. So the precision of an individual one isn't that big of a deal. So yeah, I mean, you can print arrays, you can multiply arrays. So this is the matrix product. You can do an element-wise product. Int 8 for the win, yeah, for sure. I think with int 8, I wasn't able to see 2x throughput over floating point 32, at least on BERT on CPU. I think it was closer to like 20 or 30% or something, which is, nice, but it wasn't like this big oof moment. But the error rates didn't change all that much, with that in mind. Yeah, so here, like, at is basically, I think they added this fairly recently. It just means matrix multiplication, because if you're just using the regular matrix symbol, it's going to do an element-wise product. Other stuff you may want to do with matrices is reshape them. Like, let's say you have a matrix, and then you want to turn it into a vector. Well, you could, for example, just reshape it to the length, and then that reshapes it. You may want to take a sum along some set of axes. You may want to delete an axis. You may want to delete an element. You may want to take two matrices and sort of stitch them with each other. So this is the stack operation. You may want to add an extra dimension that's empty. So that's called the unsqueeze operation. Or maybe you want to remove all you want to remove all dimensions of size 1. That's called the squeeze operation. So there's a whole bunch of these that are very useful, because it lets you treat your matrices like objects or data structures that you can manipulate. And it's a very, like, a matrix is a very general data structure, because you can, encode a graph with it. You can encode, so you can encode pretty much anything, like any relationship as a graph. So yeah, so here they talk about indexing and slicing. So this is like getting specific elements of a matrix that you may want to do something with. So this is sort of like here, the shape manipulation. You could do operations on it, like, I don't know, like round up all the elements in a matrix, like resize. What's a revel? I forgot. Returns a contiguous flattened array. Okay, so this just like flattens it into a 1D array. So for example, this is very useful in deep learning before doing a softmax layer. So you have a matrix, turn it into a vector, and then from that vector you take a softmax, and then you get a classification out of it. So this is why this comes up a bunch, at least in deep learning. I wouldn't be able to tell you why revel is useful in any other context. So here, like, other operations like vstack, for example. So notice, like, we have this matrix, and then you can stack it on top of another one, or you can stack them horizontally. Vstack and hstack obviously only makes sense in the context where a matrix has 2 dimensions. But if it has more dimensions, then you could stack along a specific dimension. And I believe PyTorch does have stuff to do so, for example. And probably so does. Yeah, I mean, you can copy matrices. You can do a shallow copy or a deep copy. So the way to think about arrays in Python, at least. Oh, so I think ravel is a pseudo word to mean the opposite of unravel. That makes a lot of sense, actually. Uh, that's actually cool. I didn't think about it. Thank you. So, so yeah. So back to this. Like, when you're thinking about what is a matrix exactly, well, in Python, it's actually just a pointer to some data that's stored in memory. And even though the matrix may look like this, let's say, so here, like basically a Python and D array is a pointer to like essentially a struct in C, right? And so in C, like there is no concept of a matrix, at least not natively. What there is a concept for is pointers, right? So let's say you want to have a 2D array. So, well, this would point to, for example, a row, and then each element of the row would point uh, to the next row, to the next column, right? So basically you have a pointer to here, and then you have pointers to all the way here, and then pointers here. So it's all pointers all the way down. And this is important, right? Because if you say something like, like let's say you make a copy of this thing, well, it's actually it's going to create like a new object versus creating another pointer to the same thing. So you have to think about this stuff a bit more in a way that you wouldn't usually need to in Python. So this is where stuff like deep copies or shallow copies come into play. Yeah, so complete array of like it's a deep copy takes actually makes a copy of the array and the data inside. And again, like if you're trying to understand like, well, why is this a thing, then if you just remember that actually you're using some assembly code or some actual layout in memory. Oh, actually, so sorry, one thing I didn't make too clear here is that ultimately if you have a matrix that looks like this, you have two indices, right? I and j. So if you do something like 2i plus j to index, then you can basically pretend like a vector is actually a matrix. So you're essentially changing the way that you would index. So basically here you would use ij, basically it would be like this, and versus here you would use just like a single thing to index into a vector. So just one thing to keep in mind. And actually, if you look at stuff like matrix acceleration on SIMD, like one of the ways in which matrix acceleration can be accelerated with SIMD is even though a matrix isn't a vector and isn't embarrassingly parallel in this way, let's say you're multiplying two matrices. So this is matrix A, and then this is matrix B, right? But in this format, then when you multiply them, you can use them with this new indexing scheme and still take advantage of SIMD acceleration. So, sorry, I've said SIMD many times. So SIMD means single instruction, multiple data, right? So what does this mean exactly? Like, what's the single instruction? Matrix multiply, right? Matrix multiply over data. So you're essentially running the exact same operation, just over different arguments. And this is just something that would need hardware support to do efficiently. But again, like, so you're gonna hear this a lot. And again, like one thing that's very humbling in deep learning is that sure there's sort of a lot of stuff that you can do, but a lot of the comes down to like this core loop that we're trying to make sure is faster than big O of n cubed, right? Um, so there's a couple of, I think, so here they talk about beginners, okay, how to install it, like what's an array. You can partition an array, you can concatenate them. It's an object, so you can do stuff like figure out its shape and stuff. Uh, oh yeah, so one important idea I think is broadcasting. So let's talk about this for a second. So let's say you have here, I think it's clearest here. So let's say I have an array, a vector that has elements in it that are 1, 2, and 3. And then I have a scalar 2. And then I want to multiply a times b, right? But remember, so here you're not really specifying, well, I want you to do vector by scalar multiplication, right? So how does the compiler actually know like what the hell you're actually doing? And so here it's sort of like where it does something a bit clever. So what it does is it's like okay, well you're multiplying you're multiplying an element. So what you're likely to be doing is probably multiplying this individual element by each entry here, as opposed to so as opposed to only multiplying it by the first one. So here it's like it's saying, for example, well, you're probably not doing element-wise multiplication, or like so over just the one, for example. So it's not like the output is going to be 2, 2, 3. You're probably going to want to do 2, 4, 6, right? And so what broadcasting does is it sort of stretches an element that where the dimension isn't long enough, so that you can sort of map the operation. So it would figure out automatically here, okay, well, I need to stretch B to be 2, 2, 2, and then I do the dot product between A and B, and that's what A times B means. So this is what broadcasting means, and there's a whole bunch of rules for when it's valid or not valid, and it is kind of a nasty source of bugs when you're dealing with PyTorch code, because often you're not thinking about, actually, you're basically misspecifying the dimensions of your data, but you're not realizing it because broadcasting is sort of helping you out. But often like this can just like cause bugs, so you can always just like not use it, right? So just sort of copy this, like make sure that this is a vector and do the dot product, as opposed to assuming that scalar multiplication works just fine. Another thing that I thought was interesting to keep in mind is that, like, well, when you're working with different architectures, let's say I trained a model on ARM, but then I'm deploying it on, so here, like, okay, yeah, so let's say, for example, I trained a model on Intel, but then I'm deploying it on a Sun machine. Well, they actually use different conventions to represent numbers, and I want NumPy to abstract this away from me. Like, I don't want to, me as a user, add to my code things that say, if this architecture, then do this, and if this architecture, do that. Like, I want, ideally, NumPy to go figure this out for me. So this is what byte swapping is about. And there's more nuance to it too. Like, for example, there's no guarantees that multiplying two floating point numbers will produce the same result on Linux or Windows, for example. So this is not something that you generally think about, but it is something these library maintainers need to certainly think about a lot, actually. So yeah, so I think in terms of the core API, like this is really what NumPy is. So I think now what we could do is we could just like quickly go over the GitHub repo and take a look at some examples of like how this all works, right? So let's say, I'm going to pick the simplest examples. I'm going to pick, let's say, the dot product, dot. Dot product is anywhere here. Product. Log factorial. Let's see, NumPy. Dot product. NumPy dot dot. Okay, great. So let's see. So where's the source? Source. Can I just like spit it out? Why can't I find dot? Dot 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 dot. Okay, let's look for it. So let's see. If I go to NumPy, for example, so let's take a quick look at like what's set up here. So we have, for example, these like the fast Fourier transform, which is useful also if you're doing convolutions, because you can implement convolutions using FFT. There's some linear algebra libraries. So for example, here, let's take a quick look at this. And I think that's a great example of the code is the documentation, right? Like a lot of times when you're figuring out like what is supported, you'll look at the docs, but I've often found like just looking at the code nowadays is a lot easier and a lot less ambiguous. So for example, like, well, we know that it works over complex types, and then we know that, like if you have a complex type, then the real number needs to be either a single or a double precision float, or it could be this thing called a C single or a C double. So these are like C data structures. And then, okay, so they have things like a fast copy and transpose, for example. Okay, here, like, let's say take the transpose of a matrix is really about swapping the axes, for example, which makes a lot of sense, right? Because transpose, so swap axes is a more general operation. So let's say we take a look at swap axes, then it's defined somewhere else. And how does swap axes work then? Okay, so it's a decorator here, it looks like, that uses this dispatcher. Okay, great. So I think we need to talk about dispatchers a bit. So let's say you have like you're multiplying two matrices, and the matrices are floating point 32. And so you wrote all this code for floating point 32. But then you also you want to basically you want the library to also work well for floating point 16. but you don't want to have to duplicate all your code. And so this is where this dispatcher pattern helps, where you're essentially going to say, well, I want you to pretend like this is sort of a number type. And then at the very end, I want you to actually use the floating point blast subroutines that are important. And this concept shows up a lot, like a lot more obviously when you're using something like Julia with dynamic dispatch. I have a blog post about that, an interactive one. So just something to keep in mind. So let's say, okay, so here we're at dot. Is there a dot anywhere? There's multi-dot. Tensor dot, okay. So let's go back a bit. So notice here, like there's the LAPACK light module, right? So this is basically uh, making the Fortran code C code. So you can basically interact with the Fortran code from C. And this involves a lot of stuff like, well, is it an int? And then what's the name? And then what are the type parameters of this? So this is like a lot of boilerplate more than anything, but it's basically just saying like, look, this boilerplate is worth it because the underlying libraries are so fast that I don't want to have to bother and go changing them. So this is a totally worthwhile and valid use of your time. So let's go to core, for example. So we should, okay, so here, okay, let's see, array. See array anywhere? Array print, that's not what we want. Get limits, multi-array, numeric.py. Okay, what's here? Okay, so for example, here's stuff like returning like returning like an empty matrix, like all zeros. There's the concept of dispatcher returning ones. So wait, where was it? Numeric types, shape. I'm still looking for dot product. So if any of you have found it, please link me. Okay, we're getting closer. So notice, for example, here, like where it says SIMD, here has like some of the operations that were. What is this thing? I found some. No, I think the Blas code made it a bit easier to understand. But like I mean, it gets very low level very quickly, right? So it's one of those things where I think the foundation is actually very solid, and so you see a lot of innovation on the outskirts, but people haven't, I think, really done too much in this space for a while. Unsigned math, loops. See how the loops work. Okay, so there's some. I can't read this. I don't even know what the fuck this is. I can't really read this. Uh, okay, I would imagine it's basically very fast for loops, and so you can imagine this is important because matrix multiplies are 3 for loops. Dot product is 1 for loop, so you need lots of for loops, and so it makes sense that this would be here and be really fast. So is it even clear that you can build something better than Blast if you put in the effort? Okay, I asked this very same question on Discord, and I need to thank NB21 here in our Robot Overlords Discord community for giving me a great answer. So he basically said that it's really hard to improve Blast performance because Blast is sort of a theoretical implementation that has the minimum amount of communication that uses the minimum amount of communication over caches and cores, right? So I think maybe one last thing we can talk about. So we sort of saw briefly like what does the numpy API look like. We saw what Blast looks like, even though we couldn't really understand what the hell's going on. But we just know that it works over multiple kinds of hardware, and that it has like basically support for doing math over vectors and matrices, and it's divided into 3 levels from vectors to matrices and vectors to matrices by matrices. And one thing I want to talk a bit about, and I sort of alluded to this idea in my deep speed video, is the tiled matrix multiplication algorithm. And so I thought this was a really clever idea, but here, let's put it this way, right? So remember when we were looking at Openblast, here, where was it? So Openblast and then kernel. Where was it? So the kernel. Yeah, so LAPACK, I forgot to talk about LAPACK actually, so I'll just say very quick words about it. I think I had a slide here. So LAPACK would be your C library for interacting with Blas, right? So the way this looks like is, again, you have a library and it tells you, okay, well, you want to multiply 2 matrices. Like what you need to know is like the op that you're running, the number of rows, the number of columns, some scalar that you're using, the first dimension that you're using. So it's a very generalized kind of matrix multiplication. And actually, I would suspect if we looked at numpy matrix multiplication, that it also has sort of a similarly long signature, right? Like it doesn't just take x1 and x2. It takes in like, well, where are you putting this thing? And then let's see. So what else is taking? It's saying like the casting, for example, like let's say you're multiplying a matrix that's floating 32 by a matrix at floating point 16. Do you want the semantics to be make it floating point 16, or do you want the semantics to be make it floating point 32? I would probably say 32 is probably a more reasonable default, but this is just something you can control here. Another one is like, well, what's the D type of the output? And then there's like some other hooks, like, well, which axes are you using? Are you ignoring some axes? So just something to keep in mind is that even though matrix multiplication is just such a basic operation, there's a whole bunch of nuance in how it works. And actually, I found this really good answer on Stack Overflow I thought we could discuss briefly. Where was it? No, it was not this one. I think it was this one. Okay. So this guy, for example, was comparing the running time of some for loops in NumPy and pure Python versus C, right? And so I think this is an interesting benchmark because it shows you, well, pure Python is very slow, but the C wasn't that much faster. And NumPy, which is actually in Python, was faster. But if you've been paying attention, NumPy isn't really a Python library. NumPy is a Fortran and C++ library with a Python like outfit to make it easier to work with. And so I thought, where was it? I think there was a really nice answer here. Right, so here they talk about how, like, for example, it uses like some core code. Wait, where was it? Yeah, and so they mostly worry about, so want to become famous by followers. Can we please ban this? I don't want to be famous. I just want to be loved. So NumPy is also highly optimized code, beautiful code. What is this book? Beautiful code. Oh, it's a whole chapter. That's kind of cool, actually. What is this book? Beautiful code. Exactly. $0. Really? Only one is truly great. Which one is truly great? Okay, never mind. We're getting distracted now. But where were we? So yeah, so we talked briefly about Lapac. And there's not really much to know. Like you can, again, Lapac is a nice wrapper for Blas. NumPy uses Lapac. NumPy also has some C bindings to make it easier to interact with Lapac. And then on top of those C libraries, NumPy has a Python front end where they try to re-implement as much stuff as possible, but really performance is key, right? So where was the thing I wanted to show you? Oh yeah, the tiled matrix multiplication, sorry. So I really like this slide because, so let me show you this example. Actually, first off, I think one thing I want to show you, so there's the Jeff Dean numbers programmers should know. All right. So cache comes up a lot, right? But a lot of times it's hard to sort of figure out like, well, what kind of order of magnitude savings are we having? If you're like me, and most of what you do is in main memory, like, you basically think about, does this fit in RAM? And if so, great. Like this is sort of like the order of magnitude that you're working over. Oh, it's Norvig, I see. Close enough. It thought like, I think they're both at Google, right? Uh, so so yeah, so we have the like here we have like main memory is 100 nanoseconds, and if you're even worse, then you're reading from disk, which is often also what we'll do in deep learning if our models don't fit in RAM. Then this is the order of magnitude that we're working over, right? But if you can make sure that a lot of stuff ends up in cache, then you're basically working in a model that's about 100 times faster. And it's a big deal, right? Because let's say in the case of deep learning, like running time, training times are very slow. So let's say you're training something for 6 months. Let's say no, for 100 days, so like 3 months. Well, you could train it in 1 day instead. And 1 day isn't that bad, like 1 day means, you run it at night and then the next day you check it out and you're good to go. You have a model that you can work with. 100 days means you need to go convince a bunch of VPs that what you're doing is important. You need to have a lot of funding. You need to make sure that there's no like failures, like etc. So it introduces like a whole bunch of complexity. So how can we make sure that we may obviously this is not going to be the amount of time that we're going to run matrix multiplication in, but how can we make sure that we as much as possible use the cache, right? And so the main trick is styled matrix multiplication, which is explained very well here. Where was it? Oh yeah, and the other thing to keep in mind is that memory hasn't gotten much faster over the years. So any improvements that you do here will make a big difference. So yeah, so one trick is pipelining here. So again, the example they give is like, well, let's say you have 4 laundromats. No, sorry, let's say you have 1 laundromat, but 4 people need to do their laundry. So you could parallelize actually how you're using the dryer and washer and who's doing the folding so that you don't have to wait for someone to finish completely before you start an operation, right? So it's like, as long as there's no dependencies, you can just start doing the washer, I guess. Though this kind of looks like a dryer to me. Right, so let's see here. Another thing to keep in mind is that here, like this is something that comes up a lot in ML compiler talks. Like ML compilers all pitch themselves in the exact same way. They're like, we do automatic quantization, so we lower the precision that you need, which means that you need some hardware that supports it. And they also say we do operator fusion, as in like, let's say you're reading something from disk and changing it, then maybe you don't need to commit it back, right? So this is where operator fusion helps. Like maybe you don't need to do these you don't need to store all your intermediate results to memory or disk, and you could just do an operation and fuse it. And so this is why this is very helpful, because it just saves you cycles and makes it so that your pipeline graph has fewer steps, which means it's easier to parallelize over more people. All right. So this was the SIMD example we talked about earlier. So remember, like Intel, for example, recently, maybe not so recently, introduced like AVX 512. So you can have you could potentially do vectorized instructions over vectors that are length 512. And so also remember, it's not just vectors, right? Because you could also represent a matrix as a vector by using like a different indexing scheme. So this really helps. And so they do this, for example, like they have their own library called IPEX where they do this kind of stuff, but then they also do automatic quantization on floating point 16 on some of the later Intel chips. So this is just something to keep in mind, in that a lot of this sort of hardware acceleration has these similar themes. Like how can you take advantage of parallelism? How do you pipeline? How do you take advantage of cache? How do you quantize? Quantize is also important for a few reasons, right? Because if like it means you need less space in memory. It means the base operation can be accelerated more on hardware. It means that like your latency can be better. So it just has like benefits all around, right? So this is again the like you have the read after write, write after read. Then maybe if you're single instruction multiple pipeline SIMP. All right, my dude. That would be a bannable offense, like if you were not the, the main mod, we needed to have a talk. All right. So back to matrix multiplication. Like you basically like we're trying to implement. So I think this is vector to matrix multiplication, right? So we're taking an entry in a vector, and then we're in the column of that vector, and then multiplying it by an entry in the row of another vector of another matrix. Uh, I think. Oh no, sorry. This is like they're doing it. This is a linear. This is a linear map. Sorry. This is like ax. This is ax plus b, right? So this is just a scalar. Like, sorry, a vector. Just I mean not a function, right? Um, so matrix multiplication naively is like we said a big O of n cubed operation. But what you can do is we could sort of divide it up into blocks, right? So here, like it's basically computing this entry means that we need to basically do all the operations on this row and this column, right? Here, let me make this a bit bigger. So what you basically need is you need to know where this row, you need to know where this thing is, you need to know where this thing is, and you need to know where the string is. So if you're actually like, think about like you're a branch predictor, right? Or like you need to figure out, like you need to build code such that like maybe you're not just loading an individual element here from disk or from from RAM or disk, God forbid, you want to like load a bunch at a time, right? So that because you know it's going to be called for in immediately the next iteration. So I mean, just as a puzzle, right? Like the next element here, is it going to be ci plus 1j or is it going to be cij plus 1? So if you can answer that question, you're getting a bit closer to thinking about how uh, linear algebra people think about accelerating matrix multiplication. All right. The algorithm I want to talk about is this blocked matrix multiplication. And again, I want to thank NB21 for sending me this reference. And like if you just look at here, like this blocked implementation seems to run about what? How much faster are we talking about? So here we have 0.001. Okay, it seems to run about 100 times faster. It looks like, I mean, obviously this is only going to make sense for larger matrices. Oh yeah, the problem size. Okay, no, I think this may be a bit easier to read. So 0. I think this is a log scale, so I'm having trouble reading it. Is it a log scale? Yeah, it is a log scale because each of these is the like multiplied by 10. But suffice to say that it is much faster. So, 100x, yeah, sure. So how does this work exactly? Where was it? Auto tuning here. All right. Okay. So imagine now that you're multiplying two matrices A and B, right? And now let's also imagine that these matrices, their sizes are multiples of 2. So they're very easily divisible. So like let's say this is A11 is a 2 by 2 matrix. And so this is 2 by 2. So we're going to have 4 and 4, right? So wait, is that right? I think it's going to be 8, right? So it's going to be 2 2. So we're going to have two elements. Yeah. So we're going to have 4. Yeah, so it's going to be 4 by 4. Sure, sure. So you basically split them according to these blocks, right? So you're going to say, okay, I'm going to have A11 and I'm going to split A12, A21, A22. But then what you do is what you're basically trying to make sure is like, let's say, look at A11, right? So A11 influences the results of which cells? It influences the results of this cell and this cell, right? And that's it. What about like B12? Well, B12 influences the results of this cell and this cell. And so whenever you access an element of this block, you want to make sure to fill in all the relevant elements of this new matrix, right? And so the idea is that like now we can rewrite matrix multiplication not as a function of individual elements, but as a function of blocks, right? And then you do the multiplication recursively. So you have like this thing, you can rewrite it as something like this. So this ends up being like the format of the matrix multiplication using blocks. And this answers two big insights. So the first one is that, well, why did Blas have all these kernels, right? Like, why did Blas have hard-coded code for 2 by 2 matrix multiplication and 4 by 4 matrix multiplication? And this is the answer. The answer is that for a generalized matrix of size n by n, you want to recursively decompose it into multiples of kernels that already exist in Blas, and then recurse back up to actually fill up all the values, right? But this also gives you another hint. Well, how does model parallelism work like in something like in NVIDIA's Megatron? And the example I want to give here is, let's say the individual matrix C is too big to fit into RAM. Like let's say, or like, I mean, not RAM, let's just say it's too big to fit on a single GPU. So it's bigger than like 40 gigs, for example, right? So if you have a matrix that's big, how can you still do multiplication over it? Well, you can. What you can effectively do is split it over multiple blocks and then do the multiplication over blocks and then aggregate those blocks onto a CPU, basically with RAM. And so this saves you from having to do all of these operations on the same device and run into out of memory issues. And it explains why Blas has core kernels for matrix multiplications with specific sizes. All right, so this is such a core idea. And also it explains another thing, right? Like when we talk about caching, well, we said we want to make sure that when we're pulling a block, that we're basically using all the elements that we're filling up all the possible outputs from that block, such that once we finish reading a block, we don't need to come back to it ever again, right? So effectively here, after doing this row, like, well, you could discard B11 at this point. I mean, after doing this thing, well, you can discard B11 at this point. So this is just something to keep in mind, like where let's say these are intermediate results, for example, and you don't need to store block as a type. What do you mean by block as a type? Block. Does it say block? Okay, I just noticed the typo. I completely missed that one. Yeah, so this is not my presentation, by the way, just to be clear. This is someone else, I believe, who is called Kathy Ellick. Who is Kathy Ellick? Oh wow, she's been doing like high performance computing, looks like, for a long time. Exascale Global Address Space, the Parallel Computing Laboratory, GAs, High Memory Genome Assembler. So notice like another thing here is that a lot of times I noticed in talking about numerical code, like sort of benchmarks are king, right? Like you can certainly assume that like your optimizations are gonna be like the latest, amazing thing that solves everything. But if you don't have a way to benchmark these things, you might as well just be speaking out of your ass, right? So this is just like something I think I've noticed that smart people are very good at back of the envelope calculations. Like they just make sanity check all of their results. And I think at this point we are pretty much in good shape, right? So I think to conclude, what did we talk about, right? So we talked about NumPy and compared it to PyTorch and TensorFlow that also add GPU acceleration and AutoGrad, whereas NumPy mostly works with tensors and matrices. Obviously, there's more stuff you can do outside of deep learning, from solving systems of linear equations to maybe differential equations or whatever, and SciPy. So this is all super important there. The core NumPy library is mostly focused around matrix manipulation, so how to multiply matrices, vector, stack, unstack, index, delete, horizontally stack, vertically stack, transpose, and all these kinds of operations. Most of these implemented in Python. There's also some code in C++, which exposes a foreign interface in Fortran, which then lets you interact with the Blas protocol. And Blas is a protocol that has different implementations on various hardware that effectively has very fast kernels to do things like matrix multiplication or vector to matrix multiplication or scalar to vector multiplication, etc. And the main ideas that are super important and that show up all the time are pipelining, vectorization, and caching. Pipelining, as in, if you have a single, if you have, for example, a single adder, that it's not basically waiting for the entire result of an instruction of a set of instructions to finish, that it can just like keep going. Vectorization is essentially taking advantage of things that are embarrassingly parallel, like a dot product. But another important trick we talked about is that if you're trying to do CPU acceleration of matrix multiplication, you can turn a matrix into a vector by using a different indexing scheme and then still use SIMD to multiply matrices. And then we also talked about how Blas has these core kernels and, for example, matrix multiplications in 2x2 and 4x4 and 8x8. And that is because the way matrix multiplication is accelerated is that we split up a matrix into several blocks and then recursively keep doing this until we hit the base case, which are those kernels that are written in assembly that are super fast, that are optimized for various hardware manufacturers, and that most people are probably not going to figure out how to make much faster, because I believe most of them are probably theoretically optimal, even, and provably so, given the communication overhead. And this also, the same trick you can use for things like scaling model parallelism, so that you can multiply giant matrices that don't fit on a GPU's memory using like NVIDIA's Megatron. So even though these ideas were NumPy specific, they are core ideas that show up all the time in numerical computing. So yeah, that was it, I think, for me. I sincerely hope you enjoyed this. Thank you so much, everyone. And if you have any other suggestions of other videos that you'd like me to discuss, please feel free to let me know in the comment section below, or feel free to join the Robot Overlords Discord and just reach out to me directly with any ideas. Thank you so much.